For our next math video, we're going to study something that is going to become more and more important as we study more mathematical cryptography. That is factoring integers and prime numbers. So the first thing we're going to do is define what it means to factor an integer. We're going to use factorization to understand and define what it means to be a prime number. Then we're going to give a new definition, or at least a new way of looking at what it means for two integers to be congruent. And then we're going to show how factorization can help us solve some more of these new congruence problems. Okay, so basically factoring a number is just writing it as a multiplication of other numbers. So for an integer, what that means is we're taking some integer n and we're writing that number n as a product of at least two integers. And I almost said two other integers, but they don't necessarily have to be different integers. So here's an example of how we can factor the number 30. We can factor it as 6 times 5. 6 and 5 are integers, and 6 times 5 is 30. We can factor it as 10 times 3. We can factor it into more than two numbers. We can factor it into three numbers, 2 times 3 times 5. And we can do ridiculously boring factorization like 30 times 1. This is one of the reasons I didn't want to say factor it as a product of two other integers, because it could be the same integer times 1. The next question I want to ask is, what does it mean when we say we want to factor a number, or in particular factor an integer, as much as possible? Well, let's see what happens when we try to do that to 90. So one way we can factor 90 is at 10 times 9, but I would say that that's not the furthest we can go in factoring it, because we could, for instance, we can factor 10 into 5 times 2, and that in some sense factors it further. And we can go one step further. We can factor the 9 into 3 times 3, and so we end up with 5 times 2 times 3 times 3. Now once we get there, in some sense, we can't really factor it any further. And the reason we can't is because the factors that we have in there, the 5, the 2, and the 3, those are all prime numbers. So what's a prime number? Well, basically that's a number that can't be broken down any further by multiplication or by factoring. So a prime number is some positive number integer p that has exactly two factors. Namely, those two factors are p and 1. If it had any other factors, you could use that factor to break down p. So prime numbers can't have more than those two factors. Now, one thing that we studiously did in this definition, and this may seem unfair, is we defined this specifically so that we can exclude the number 1. Now, I love the number 1. It's one of my favorite numbers, but it doesn't work so great as a prime, and let me explain why. So first of all, we can add 1 to any factorization, and it doesn't really change it in any kind of meaningful way. For instance, if we take the number 4 and we break that down into 2 times 2, that is a meaningfully different factorization. But if we want to be smart alecks about the whole thing, we could take that 2 times 2 and just add a factor of 1 in there, 2 times 2 times 1. Now, if we considered 1 to be a prime number, that would be a different prime factorization. But if you're looking at it, you say, well, that's not any different really than just 2 times 2. And not only that, we could add a whole bunch of factors of 1. I can add another one, 2 times 2 times 1 times 1. So we have infinitely many factorizations of 4 with those extra 1s on that don't really do anything to help us understand 4 any better. The second reason is, remember, one of the things that was really important to us is that primes couldn't be broken down into other numbers, right? But if 1 is allowed to participate in a prime factorization, then 1 itself can be broken down. We could just write 1 equals 1 times 1, right? 1 is broken down into two primes, 1 times 1, and that wouldn't be allowed as a prime number. So either way, 1 is a great number. I love it. It's a wonderful multiplicative identity, but it doesn't participate well as a prime number, and that's why we exclude it. All right. The next I want to talk about what a prime factorization is, and all that is, and we've actually done this in one of the previous slides, is when we factor a number into just prime factors. So remember with 90, we factored that into 2 times 3 times 3 times 5. Those are all prime factors. There aren't any non-prime factors in there. That is a prime factorization of 90. And what this can do is it can help us solve certain integer problems. One of the problems that it can solve is one that I asked you to do with the number 210 on one of your in-class activities, finding all the factors of a number. Having all the prime factors helps us organize how we find those factors. So let's see what we can do for 90. So I'm going to organize this in terms of, if I have a factor of 90, how many prime factors are in that number? And it may seem like I should start with one prime factor, but actually I'm going to start with 0 prime factors with the number 1. That's the only one with 0 prime factors. So 1 is a factor of 90. Now I'm going to look for all the factors that have just one prime factor in it, and that's just going to be the primes 2, 3, and 5. Now if I do 2 prime factors, I got to be a little bit more careful. If I look for the ones with 2, I get 2 times 3 and 2 times 5. And then if I look at the ones without 2, that just leaves 3 times 3, right? There's 2 factors of 3, and then 3 times 5. If I want 3 prime factors, I start with 2 times 3 times 3, and 2 times 3 times 5. That's all the ones with 2 in there. If I exclude 2, that just leaves 3 times 3 times 5. And then there's one with 4 factors of 4 prime factors. That's 2 times 3 times 3 times 5. And then we just multiply all those suckers out, and those are all the factors of 90. A lot easier than saying, is 1 a factor? Yeah. Is 2 a factor? Is 3 a factor? Going all the way up to 90. It enables us to focus our search. The last thing I want to talk about is factoring and how it relates to congruence. Okay? But before I talk about factors, I want to talk about one more way that we can understand congruence. So let's say we have the statement A is congruent to B mod n. We have two different ways that we understand that so far. The first way is the kind of days of the week or hours in a day type of model. It says there are n days in a week, and then A and B represents the same day of the week. And as I mentioned, if you like the clock analogy, that's fine. Or if you like the date of the year, that's fine too. Anything that helps you understand, anything that has a cyclical nature is a perfect way of understanding congruence. The other way was more abstract, right? That was looking at it in a sort of a quotient remainder form. A is equal to nq plus b, where q is some integer. So we can kind of think of B as a remainder, but remember, when we're talking about congruence, that remainder doesn't have to be smaller than n. So here's one more way we can think of A being congruent to B mod n, and I'm going to use that second equation to help us do it, that A equals Qn plus B. Now if I move that B over to the other side of the equation and sort of flip it over, the equation is very equivalent to Qn is equal to A minus B. And what we've done is we've written A minus B as a multiplication of 2 integers, Q and N. And that tells us that N divides evenly into A minus B. Right? And so that's our third understanding of congruence. A is congruent to B mod N is exactly the same as N divides A minus B. And just to give you some context for that, you've actually kind of used this one in some of the congruence problems that you were doing before. At least some of you have, because you looked at, well, A is one day, B is another day. How many days are there in between? Are there a whole number of weeks? And N dividing A minus B is exactly that. A minus B is the number of days between A and B, and N dividing that says that it goes in a whole number of weeks. Anyway, just to give you a little context there. All right, so we're going to use that to solve the following little math puzzle. So suppose we have mystery numbers A and B. I'm not telling you what those numbers are because I am a jerk. And all we know about those numbers is they're congruent to one another mod 90. So A is congruent to B mod 90. Can we fill in A is congruent to B mod anything else? So I want as many of those question marks filled as possible. Is A is congruent to B mod 5? Is A is congruent to B mod 13? Who knows? I'm gonna see what all those numbers are going to be. So here's what I know from our new understanding of congruence. I know that 90 divides evenly into A minus B, and that tells us that A minus B is equal to 90 times some integer, and I'll call that integer Q. Well, we can factor 90 into 10 times 9. Here's where the factoring comes in, and put that back into the equation. That tells us that A minus B is equal to 10 times 9 times Q, which tells us if I move the 9 and group it with the Q, I know that A minus B then is equal to 10 times the quantity 9 times Q. Now, one thing I know about 9 times Q is Q is an integer, 9 is an integer. That means 9 times Q is an integer. And if I look at that equation in that context, that tells me that 10 divides evenly into A minus B. 10 times some integer, 9q, is equal to A minus B, so that means 10 divides evenly into A minus B. But with our new definition of what it means to be congruent, that tells us that A is congruent to B mod 10. So 10 is one of those question marks that we can fill in for our mystery numbers. Now, there was nothing special about 10 except that it was a factor of 90, right? We were able to factor 90 into 10 times 9 and then use that to show that A is congruent to B mod 10. You can do that with any factors of 90. If you want to do it with 2 times 45, you get A minus B is equal to 2 times 45q, and that would tell you that A is congruent to B mod 2. So that tells you that if n is any factor of 90, then A is congruent to B mod n. All right, so now that you've kind of messed around with this one, let's see if you can work on some of those activities for factoring and prime numbers on the PDF file included with this video.